Hello everyone and welcome to this video lecture on inverse trigonometric functions. Now this video is specifically pitched at my students at the University of South Florida. We were working on inverse trig functions this past week, which would be section 4.6 in our notes, and we got some of it done, but not all of it. So I'm making this video as a supplementary lecture to make sure we get through all the information and that you are all prepared for upcoming exams. Now, if you happen to be a passerby, somebody who saw the video and thought, I'd like to learn more about inverse trig functions, don't worry. We are going to be providing enough background information that this video should act like a standalone lecture, and as long as you follow along with me, you take notes, you actually try to work through the examples, you should walk away with a decent understanding of what's going on. However, from what I've said, there are some things that should be known up front. First of all, I must really like you USF students because I think I've redone this video about 73 billion times. That's the nature of recording videos. That's just how it is. And this time around, I think I'm probably going to record it and post it warts and all. So if you hear me say something especially funny, you know why. The second thing you should know is, since this is going to be kind of like a standalone video, I am going to put in some background information. However, because this is going to be primarily supplementary lecture material for my students, what that means is the background material is going to be gone through pretty quickly. For example, I have some reminders on this page, and I am going to go through those reminders. However, they're going to be pretty fast. The next couple of pages are going to have some reminders and some formulas that they should already have seen and should already know, and we're just going to pass through them swiftly so we can move to the examples, which are going to be our primary objective. With that said, make sure that you have something to write with next to you. Make sure that you have your notes or a good textbook or that you are very comfortable drawing the original 6 trig functions, and let's go ahead and begin. Whenever I start talking about inverse functions of any kind, I like to throw this diagram up on the screen. It does not actually serve as any kind of definition, but it is a nice cartoon that kind of helps to encapsulate a lot of information, and I'm going to go through that information quickly now. So, if you have a function like the one we've shown here, f, which has an inverse, which we would call f inverse, which is what we've written here when we write f with -1 like an exponent, it does not mean a reciprocal, then what should happen is we should find that f takes inputs x in a set A to outputs y in a set B. And f inverse should do exactly the opposite. If you want to think of these using real-world examples, one that is near and dear to my heart is the example of crimes and detectives. Don't ask me why that is what comes to mind, but it fits very nicely. You see, x, the input in that case, would be kind of like the culprit who is going to commit the crime, the opportunity to commit the crime, the tools, all the things that go into actually doing the crime before it's done. The function f takes all of those pieces parts and actually commits the crime, and y is the result of the crime. The detective then is played by f inverse, and it starts at the crime itself, what has happened, what the clues are surrounding the crime, and attempts to deduce from that information who the culprit was, what the means, motive, and opportunity were, etc. That is the relationship between a function and its inverse as pictured here. From this diagram, then, we have several things that we should note down. They are shown here, but we need to say them a little bit more carefully. The first concerns domain and range. The function f has a domain of A and a range of B, meaning that all the inputs for f belong to the set A, and all the outputs for f belong to the set B, as you can see here from our diagram. Our diagram also says now, when you look at it, that the domain for f inverse ought to be B. The things that we plug into f inverse all sit in the set B, and the things that come out of f inverse all belong to the set A, so that means the range for f inverse is A, which you'll notice is the reverse of what we had before. That's very natural. That's exactly how inverses and functions work. Another thing that we can learn from looking at the diagram, but which we have to be careful about, is some equation properties of these functions. The first one on the left-hand side says, if I feed an output y to f inverse, I'm going to get an input for my function f. If I feed that input to f, the result is going to be y again, just like what I plugged into f inverse. Similarly, If I plug the input x into f, I'm going to get an output. If I feed that output to f inverse, I should come back to the original input x. Now those two equations really mean follow the arrows in my diagram. If I start at y, feed it to f inverse, and then feed that to f, I come back to y again, exactly like my equation said. If I start at x, feed it to f, and then feed that to f inverse, I come back to x again. So we've kind of already got it in the picture. Another good reason to have the picture hanging around. It says the same thing, but it looks nicer. The other equations we're interested in, on the right-hand side, are what we would call equivalent equations, meaning they mean exactly the same thing. F of x equals y and f inverse of y equals x are exactly the same information, and we've noted that with this double-ended arrow in between them. If you want to think of it this way, they are just different perspectives on the same information. If I'm talking about myself, I might call myself Dr. Forrest or Zach. If somebody else was talking about me, they might say he is Zach, or they might say he is Dr. Forrest. Same information, but from a different perspective. And that's what these equations say. Whether you come from the perspective of f or the perspective of f inverse, this is the same information. The final thing that we need to include is a function f which has an inverse must pass the horizontal line test. Now, what does that look like? Well, if I take a couple of basic functions, you can see one of them is a straight line and one of them is a parabola. A function that passes the horizontal line test should see the following. If I draw any horizontal line, it should do one of two things. Either it should fail to intersect the graph of my function entirely, or, like you see in my picture here, it should intersect the graph of my function precisely once. This must happen for every single horizontal line I draw. As you can see with the straight line, this works. Every horizontal line I draw passes through my line precisely once, and that's okay. If you look at my parabola, though, we're not so lucky. Yes, there are some horizontal lines that don't pass through the graph of my parabola. Yes, there is a horizontal line, it's the x-axis, that only touches my parabola once. However, because I can draw a horizontal line, just one, that does not intersect once, it intersects twice, that means that my parabola does not pass the horizontal line test. From this horizontal line test, you can usually learn some information. As we said, an inverse function that has an inverse must be able to pass the horizontal line test. The flip side of that is, if a function does not pass the horizontal line test, then it should not have an inverse. Now you may be thinking to yourselves, now hang on, the graphs of trig functions should not pass the horizontal line test. Trig functions are periodic, they repeat themselves over and over and over again, so if I draw a horizontal line, I should intersect more than one point on any trig function. And you're right. This is 100% true. But luckily, there is a way to get around that, and the way to get around that appears on the next page. Now, before we get started, I will admit this is a very dense page of information. You can see that from just this little excerpt that's on the screen right now. And as I mentioned, we are covering 6 functions, 6 inverse functions that we need to be worried about. But there's a couple things I would say to that. First of all, anytime that you feel like you need a break, pause the video and take a break. Walk away for a few minutes, stretch your legs, go to the bathroom, have a snack. Come back when you're ready. It'll still be here. The second thing I'll say is, although I am going to pay some attention to sign, and there are a couple of occasions where I may have to draw a graph potentially, I am going to, for the most part, introduce the critical information for sign, and from that point onward, because, as you can already see, this information kind of repeats as you go through, I'm going to indicate where things are a little bit different, or explain why they are different, so it won't be quite as dense as it looks here. This is mostly for completeness of notes. So saying, let's look at sine. Now, as we said, sine does not pass the horizontal line test normally. However, if I restrict sine to a subdomain, meaning instead of working with all of the possible inputs, I only work with the inputs between negative pi over 2 and pi over 2, which, for those of you who are visually minded, if I draw the unit circle, means I am talking about only those angles in the right-hand half of the unit circle, since we know that negative pi over 2 is down below on the y-axis and pi over 2 is up above on the y-axis. Then we have a one-to-one function. Once we have a one-to-one function for sine on this subdomain, we can define arcsine and inverse. The inverse then has to satisfy a couple of equations, which shouldn't be surprising after our previous page, and they are sine of sine inverse of a number a should just give us a back again, and sine inverse of sine of an angle theta should give us the angle theta back again, but there are some caveats. A really here is the output of sine. It is one of the outputs that sine gives us because, remember, when we're working with a function and an inverse, we're going back and forth between the inputs and the outputs. That means that a has to fall into the interval from -1 to 1, and that is also the domain for arcsine, or inverse sine, however you prefer to say it. Theta is going to have to be between negative pi over 2 and pi over 2 because that's the restriction we had to make in order to get this arcsine to begin with. And negative pi over 2 to pi over 2 is the outputs for our arcsine, meaning it is the range. Similarly, if we move on to cosine, by restricting cosine to 0 to pi, which in our picture corresponds to the upper half of the unit circle, up top, it turns out that we can make arc cosine the inverse cosine, and it satisfies similar equations to what we saw up above. The big difference being that while a still needs to be between -1 and 1, so once again the domain for arc cosine is -1 to 1, the range now is from 0 to pi. Moving to tangent, I think it's helpful to see a basic sketch of what tangent looks like. So, I have sketched one cycle of behavior for tangent. You'll notice I've included its vertical asymptotes, which we know for probably the easiest to work with full cycle of tangent happen to be at negative pi over 2 and pi over 2. This explains why, when we move to the subdomain for tangent, the one we have to restrict it to, it is from negative pi over 2 to pi over 2, kind of like with sine, but we have to exclude the endpoints, because those endpoints are asymptotes, so we can't include them. Once again, once we make the restriction, we can define arctangent, the inverse function, and it satisfies the equations, but now the number a can be any real number. It can be anything from negative to positive infinity, specifically because tangent goes from negative to positive infinity. And theta must be in the restricted domain from negative pi over 2 to pi over 2. These first three are all pretty straightforward. The next couple are cosecant and secant. Now, in my classes, we haven't talked about cosecant and secant except in passing, so I think the most useful thing I can do to begin with is just provide you with a basic sketch of how I get their pictures. To do this, I begin with graphs of sine and cosine. I've only drawn a little bit of them because I'm only going to work with a relatively small amount of them, and I make an observation. Cosecant is the reciprocal of sine, as long as sine is not equal to 0. That means whenever sine is not equal to 0, say, for example, when sine is equal to 1, cosecant is found by taking 1 and dividing it by the value of sine. So, when sine is equal to 1, cosecant is also equal to 1. It is 1 divided by 1. When sine is equal to -1, cosecant is also equal to -1 because you will take 1 and divide it by the value of sine, 1 over -1. Any time that sine is 0, well, then we're going to have to put in a vertical asymptote. From here, we draw this strange-looking function. Wherever it is above the x-axis, it cups upward. Whenever it is below the x-axis, it cups downward like so. Similarly, if we do this for secant, we can label the points where secant is equal to 1 and -1. We can label where the vertical asymptote should be, and once again, we get these funny little cupping shapes. Above the x-axis, they go up. Below the x-axis, they go down. And it's because of these funny shapes that we wind up getting the restrictions that we do. So you'll notice we have to restrict cosecant to the subdomain from negative pi over 2 to pi over 2, which is a lot like sine, except we can't include 0, because 0 is an asymptote in our picture. Otherwise, it should be the same subdomain. Once we do that, we get the same basic equations like what we would expect. The difference is, first of all, we have to restrict theta to that weird little subdomain from negative pi over 2 to pi over 2, but don't include 0. Second of all, we have to say that a is from negative infinity to negative 1, or it is from 1 to infinity. And that comes directly from this cupping behavior. You'll notice that we never find secant between negative 1 and 1. It is either negative 1 and below, or positive 1 and above. And that explains why a is in this funny-looking interval here. Once again, we are looking at the domain and the range for our inverse function. Similarly, when working with secant, we find out that we really want to mimic the behavior of cosine. It's just that if we go from 0 to pi, we're going to wind up with this vertical asymptote in the middle. So we go from 0 to pi and remove the vertical asymptote at pi over 2. After that, we wind up with the standard-looking equations. We get the domain of arcsecant, which is, again, from negative infinity to negative 1, and from 1 to infinity. And we restrict theta from 0 to pi, excluding the asymptote pi over 2. After these two functions, I would say that cotangent is relatively quite easy. Once again, let me go ahead and sketch cotangent. Cotangent has a very similar shape to tangent, the difference being tangent increases over its cycle, whereas cotangent clearly decreases. Cotangent has an asymptote at 0 and another asymptote at pi, and this explains the subdomain. We're going through a full cycle of behavior from 0 to pi, but not including the asymptotes. Once we do that restriction, we are able to put down these predictable equations. Once again, cotangent goes down to negative infinity, up to positive infinity, so a must belong to negative infinity to infinity, and theta must belong to 0 to pi. And these are, once again, let me go ahead and state it over and over again, these are the domain and the range of arc cotangent. We're going to need these domains and ranges, and this is why I've labeled them this way. Now, at this point, we are almost ready to do examples, which is, of course, the thing we want to do most. But before we do that, we have one more page of information we need to go over, and it's just to prepare you for the examples. I have some major equations for each of the 6 inverse or arc trig functions. Now, at this point, I would say just pause the video and write them all down so you can refer to them later. I will also say to you, these are not the only ones. There are some others. For example, for USF students, in our textbook, you will quickly find that there are more equations. You'll notice that I have green equations that talk about what arc sine, for example, does with negative a, but I haven't done that for arc cosecant. There is an equation for arc cosecant that looks kind of similar. However, I have not included it. The reason for that is actually pretty simple. When I'm working with these inverse trig functions, these are the ones that I use predominantly, the ones in black. Sometimes I will use the green ones. Mostly the green ones will be taken care of by sketches, as I'll show you when we go through the examples. But I include them both because I can match up these equations with the sketches that I draw later on when we get to the examples, and also because sometimes the homework software will ask you to use one of these equations, so it's important to have them in front of you and to think about them and know what they are. Now, I don't want to beat a dead horse with these equations that I've written up here. I am 100% confident that all of you can read the equations that I've written. So, what I'm going to do is I'm simply going to summarize the information that you see here. Once again, kind of like we talked about on the first page, whenever I have a function that has an inverse, even if I had to do a little bit of restricting in order to get to this point, I can write information about the functions two different ways. I can either say the function of an input is equal to an output, or I can say the inverse function of the output is equal to the input. The only rule here is A must be in the domain. So if you go back to the previous page and look through that whole list of functions and definitions there, whatever the domain is for your particular inverse trig function, a must be in that domain, and theta must be in the range. If that doesn't happen, these equations that I've written here don't make any sense anymore and they can't be used. So you have to keep that in mind when you're working on these things. As long as we have that information here, I think that we are ready to do our very first example. Now, for those of you students at USF, you will notice that I have done probably a whole bunch of problems at this point that look like the one I've done here, calculating arc sine for various values here. I still want to include it in our notes because I feel like it is important to do these examples over and over again until it clicks. Also, we have not used these particular values, so this is good practice. I'm going to go ahead and start with the positive value for a. So I am going to start with sine inverse, arc sine of root 3 over 2. And the very first thing I'm going to do, we've mentioned this in class, is I'm going to double check that this value actually belongs to the domain. Now, I happen to remember the domain for arc sine. Go back if you don't. But arc sine has a domain of -1 to 1. And a little bit of calculation, if you have to put it into a calculator, will show you that root 3 over 2 belongs to that domain. So it is okay to talk about arc sine of root 3 over 2, and we should get an answer. For now, I'm going to put theta in the answer's place. Theta is just a dummy variable, meaning not that I'm a dummy, or at least I hope I'm not, but rather that I'm filling in the space, because now that I've written the equation, arc sine of a number equals theta, which is kind of like the right-hand side of this major equation up here, I can now write the other perspective. The other perspective would be, if I take sine of theta, I should be getting root 3 over 2. So what we're looking for now, just to make sure you remember, is an angle theta. The angle theta has to be in the range of arc sine. Again, I'll let you go back and check, but the range for arc sine should be the right-hand half of the unit circle, from -pi over 2 to +pi over 2. So, are there any angles between -pi over 2 and pi over 2 that give us root 3 over 2 when I plug them into sine? Absolutely. If you recall, sine of pi over 3, which in other words means sine of 60 degrees, is equal to root 3 over 2. In fact, if you look through the right-hand half of the unit circle, meaning quadrant 1 and quadrant 4, you're going to quickly find out that that doesn't happen anywhere else. Pi over 3 is the only angle for which sine gives us root 3 over 2. So, with this in mind, there's only one possible answer for theta. As long as theta is following the rules, as long as theta belongs to the range of my arc sine, theta must be pi over 3. Let's scoot down a little bit. I'm going to change colors to blue, and we're going to do this again, but now we're going to do it for the negative value. So we will say we're taking arc sine of negative root 3 over 2. Once again, negative root 3 over 2 is in the domain of arc sine. It is between -1 and 1. So I'm going to put a dummy variable. Once I have written an equation, I'm going to write the other perspective on that equation. That, if I take sine of whatever this angle is, I must be getting out of it negative root 3 over 2. And I'm going to stop and think about this one. For this one, I really need to have a diagram, so I'm just going to really quickly sketch one. Now, last time, when we were drawing things, we wound up with an answer, an angle, that was in the first quadrant. You should go and check this for yourself, but pi over 3 is definitely in quadrant 1. And that makes sense, because in quadrant 1, every single one of the trig functions is positive. However, this time around, we're getting negative answers. Since we are stuck with the right-hand side of the unit circle between -pi over 2 and +pi over 2, there's only one place where this angle can live, if it is going to make any sense, and that angle is here in quadrant 4. Specifically, we must get to it by rotating the wrong way into quadrant 4. Now what angle could do that? Oh, now wait a second. If I rotate into an angle like this in quadrant 4, notice sine of pi over 3 is positive root 3 over 2. And what that's implying to us is, because of the way sine works, because sine is an odd function and it goes positive when I go this way but negative when I go this way, if I take sine of negative pi over 3, I must get negative root 3 over 2. Because of that, and because, kind of like last time, if you start checking around, you find out that there is no other angle between negative pi over 2 and pi over 2 that gives me this result, it must be that the answer for this particular equation is that theta must be negative pi over 3. Or in other words, arc sine of negative root 3 over 2 is equal to negative pi over 3. Now I want you to take a look at these answers. Last time, when I took arc sine of root 3 over 2, I got pi over 3. This time, when I took arc sine of negative root 3 over 2, I got negative pi over 3. That is exactly what this green equation says here. If I take arc sine of the negative of a, then the result must be the negative of whatever arc sine of a gave me. In other words, we've just recreated the green equation for arc sine. We've just done it using diagrams and using our work here. That should not be too surprising. Okay, let's go ahead and do another example. In fact, we're going to go ahead and do the same exercise again, but this time we're going to work with arc cosine instead of arc sine. Now, I'm going to go ahead and show the steps again a little bit faster, but after we do this example, I'm going to speed things up a bit. So be prepared. Make sure you're taking notes here. Once again, I'm taking arc cosine. I'm taking it of, let's say, the positive first. I'm checking to make sure that root 3 over 2 belongs to the domain. It does. We happen to know the domain for arc cosine and arc sine are identical. And we're setting up our dummy variable so that we can rewrite our information from the other perspective. That is, for this first equation to be true, it must also be true that cosine of the angle theta, whatever theta is, must be giving us root 3 over 2. This is going to give us a different answer than last time. However, if you start looking through the range for arc cosine, which I will remind you is the upper half of the unit circle, first of all, because we have a positive answer here, we must be talking about an angle in quadrant 1, because quadrant 2 is where cosine is negative, or I should say one of the places where cosine is negative. Second of all, I happen to know from experience that 30 degrees, which is to say pi over 6, is an angle for which we get root 3 over 2 when we plug it into cosine. And in fact, it is the only angle in the upper half of the circle that does that. So it must follow that theta is equal to pi over 6, 30 degrees. Giving myself a little bit of room. If I do the same thing again, but this time with my arc cosine of negative root 3 over 2, I check my domain considerations. They're good. I write an equation with a dummy variable so I can write my other perspective. I note, looking at the second equation, that cosine of theta is giving me a negative, and since we are restricted to the upper half of the unit circle, which is quadrants 1 and 2, this implies to me that theta must belong to quadrant 2. So the question then is, what is an angle in quadrant 2 that does what we want? Well, last time when we were working with arc sine, I didn't say the word reference angle, but I'm going to say it now. Because here's what I notice. If I draw an angle in quadrant 2, this will be my theta right here. I will get negative as I wanted. If I want to make sure that cosine of theta gives me negative root 3 over 2, one thing that I could appeal to is reference angles. I already know that cosine of pi over 6 gives me positive root 3 over 2. So if I ensure that the reference angle for theta is pi over 6, then cosine of theta should basically be the same as pi over 6, except because it is in quadrant 2, it will be negative. So here's a question. What angle in quadrant 2 has a reference angle of pi over 6? Well, there's actually a pretty easy way to set that up and figure that out. Since we are drawing an angle, theta, here in quadrant 2, and since the reference angle that we've indicated is between theta and pi, we could always set up an equation that looks like this. When I take pi and I subtract theta, I should get pi over 6, the reference angle. If we solve this for theta, we wind up finding that theta must be equal to pi minus pi over 6. And if you run the calculations on that, that means theta must be equal to 5 pi over 6. So, coming back up to my work, I write down, well, cosine of 5 pi over 6 is equal to negative root 3 over 2, as desired. So, we must find that theta is equal to 5 pi over 6, and that completes the exercise. Now, last time when we got to this point, we compared our answers. Last time we found arc cosine of root 3 over 2 was pi over 6. This time we found arc cosine of negative root 3 over 2 was 5 pi over 6. Really, the comparison, though, is between the previous answer in red and what we wrote down here below our sketch. You notice that when we figured out what theta, what our answer would be, we had to take pi and subtract pi over 6. Or in other words, we had to take pi and subtract our old answer. Well, if we go back up again, you'll notice that the companion equation in green for arc cosine is, if I want to do arc cosine of the negative of some number a, I can find it by taking pi and subtracting arc cosine of a. For us, that means arc cosine of negative root 3 over 2 is the same thing as pi minus arc cosine of positive root 3 over 2. And you'll notice that we've recovered this property as well. It's one of the reasons why we really don't need those properties, even though it's good to talk about them. We can reproduce them even without having to have the formulas in front of us. Let's do an example for arctangent. You'll notice in this one I've only given one value that I want to check. I wanted to make sure we speed things up. I think by now you should be getting the gist of how we do these things. So in fact, as I promised, I'm going to do this kind of quickly. Pause the video and try to see if you can fill in the gaps that I'm about to fill in and see where you are. Okay, basic stuff out of the way. We know that the domain for arctangent is all real numbers, so there's really nothing to check there. If we write the dummy equation and then write the other perspective, we find that tangent of theta should be equal to negative root 3 over 2, and once again, we're dealing with a situation where we must have an angle in a different quadrant than quadrant 1. We know that tangent is going to be restricted to, an arctangent has a range of negative pi over 2 to positive pi over 2, and clearly if we were in quadrant 1, we would have a positive result. Since we're getting a negative result, this must mean that we are going to be dealing with something in quadrant 4 going in the negative direction. Sketching out a picture, as I'm wont to do when I need some ideas, I must be talking about an angle somewhere down here, like so, going this way. Now, I have to think through some of my reference angles here. I need to think through the basic angles, like the quadrantal angles, those would be big ones for me, and then the angles pi over 6, 30 degrees, pi over 4, 45 degrees, and pi over 3, which is 60 degrees. And as I think through those, I have a recollection. I recall that the angle pi over 3, in other words 60 degrees, has an x-coordinate of 1/2 and a y-coordinate of root 3 over 2 on the unit circle. Since tangent is given by the y-coordinate divided by the x-coordinate, this tells me, with a little bit of simple calculation, that tangent of pi over 3 must be equal, or excuse me, tangent of pi over 3 must be equal to positive root 3, which is almost what we want. Here's another observation. If you notice, if I were to make this angle in red, the one I'm trying to figure out, negative pi over 3, notice that that would mean that these two angles, the pi over 3 and the negative pi over 3, should be direct reflections of one another across the x-axis. Whenever that happens, we know that the y-coordinate would change. So we would have still 1/2 for the x-coordinate, but now a negative root 3 over 2 for the y-coordinate. Since the y-coordinate is negative and the x-coordinate is positive, this implies that tangent of negative pi over 3 will be a negative number, but otherwise it should give us pretty much the same answer. So in fact, what we figured out from this diagram is tangent of negative pi over 3 gives us the value we want. Listen to that. My dog is celebrating in the background. You go, girl. And that must mean that theta is equal to negative, or excuse me, A. No, I was right the first time. Man, I got distracted by the dog. What can I say? Dogs distract people. Theta must be equal to negative pi over 3. And there you go. We've got our example. Now that we have the basic examples for arcsine through arctangent, I want to do a couple of problems for the other weird functions. Part of this is because they are a little bit weird, but also to show you the rules that I use for evaluating them. Oh, she's singing now. That's very sweet. All right, sing us into the next problem, oh sweet doggo. Okie dokie. We have our next example. Calculate arcsecant of 2. Now, I'm going to leave it up to you to double check that 2 falls into the domain for arcsecant. You've got to get used to doing this for yourself, so I'm going to go ahead and let you do that part. I'm also going to use this time to remind you, once again, just like with all the previous examples, we must have another perspective that we can write. And I guess more accurately, what I really want to do is to take this to remind you, you should be getting used to writing these yourself. I've taken the liberty of doing it here. Make sure that you're writing these yourself. Now, what I need to do from here is a little bit different from the last few times. I really don't want to have to work with secant because secant is a bit weird, being a reciprocal function. So instead, I'm going to make an observation. If secant of theta is equal to 2, because I know that cosine and secant are reciprocals of one another, it suggests that cosine of theta must be equal to 1/2. If we can work with cosine of theta is equal to 1/2, well, that's a much easier situation to work with. In fact, if you know your basic reference angles pretty well, then you should know which angle to look for. Reaching through my memory here, I recall that cosine of pi over 3 is equal to 1/2. I am that good. I think it should be recorded on video. But on top of that, you can actually see up above, I drew the angle pi over 3, and look, the x-coordinate is 1/2, and cosine is the x-coordinate of points on the unit circle. So, with that information in tow, I know that cosine is of pi over 3 is what I want for this line. Since pi over 3 makes cosine equal to 1/2, it also makes secant equal to 2. And it's the only angle that does that in, well, in the range that we're looking at. Which we should go ahead and write down because I realized I hadn't written that down. The range that we're looking at should be the upper half of the unit circle except for the line where theta is equal to pi over 2. So, Since this is the only angle that's going to give us a satisfactory answer, it follows at once that our answer to the problem is that we must be getting pi over 3. Secant inverse of 2 must be equal to pi over 3. We're going to do this again. Let's go ahead and do it for cosecant. All right, if we're doing this problem for cosecant, we have to do a lot of the same setup. We are going to have to start out and verify that 2 does indeed belong to the domain of cosecant, arc cosecant, I should say. Let's be precise here. We are also going to have to write the other perspective equation, and we're going to have to write out another equation. This time, because cosecant is the reciprocal of sine, it won't be cosine of theta that we want to work with, but sine of theta. So I'm going to let you go ahead and write that stuff down. I'm going to return with my answers in just a moment. We're back. So you can see how I've written everything down. You see that we should be finding out that whatever our answer is, if I plug that angle into sine, I should be getting 1/2. And I know that when I'm looking at arc cosecant and its answers, the result should be somewhere on the right-hand side of the unit circle, excluding the line where theta is equal to 0. Now, once again, I've chosen this value 2, so I get 1/2, and that's because 1/2 happens to correspond with one of our common reference angles. Specifically, if you do a little bit of calculation, you'll find out that sine of pi over 6, sine of 30 degrees, is equal to 1/2. And so the answer we should be getting for this problem is pi over 6, predictably. This shows you, between these two examples, the basic theory as it applies to arc cosecant, arc secant, and even arc cotangent, although I will leave that example for you to try out. What you really need to do is get to the point where you've written the second perspective on the same information, then rewrite the equation using the reciprocal function. For secant, that's cosine. For cosecant, that's sine. For cotangent, because of the reciprocal identities, you're going to have to go and look those up in the textbook, but because of the reciprocal identities, for cotangent, that will be tangent. Once you write that equation, you will know what to do from there. This should be enough examples of this type of problem. Let's move on to some more challenging and more interesting ones. Scrolling down just a little bit, we have our next problem. We want to calculate sine inverse of sine of pi over 3. And this is one of the common types of problems you're going to run into when you're doing your homework problems. We have to figure out how to evaluate this. Now, there is a fast way to do this, and so I'm going to do the fast way because I think it will help you remember some important properties. But if you remember, I'll just put this here as a little reminder to go back to that second page of notes that we made apparently eons ago. When I take sine inverse of sine of an angle theta, the result is going to be theta if theta is in the restricted domain. Well, I guess I should say either in the subdomain for sine or in the range of arc sine, which in our case means between negative pi over 2 and pi over 2. We wrote this down on the previous page when we defined these functions, and it's important here because as I look at my problem here, I realize pi over 3 is in this interval. Specifically, pi over 3 is a quadrant 1 angle, so it makes perfect sense that it should be less than pi over 2, and it's definitely bigger than negative pi over 2. With that said, I really don't need to do any calculation. The answer is just pi over 3. But I would also like to go ahead and sketch a really quick picture for you because I think it helps to illustrate something we're going to need in a moment. All right, I have gone ahead and drawn the angle pi over 3, and I've included also its terminal point, and here's why I say that. Remember that what's happening here is we are basically going through steps. If we were to follow our diagram like we did on the first page, what would happen is we would first plug pi over 3 into sine, and it would take us to this value here. Then what we would do is we would want to find an angle that gives us this value when we plug the angle into sine, which must be the angle that goes along with it here in my drawing. Now, it's kind of useless here because we have this nice information. Sine inverse of sine of theta equals theta, specifically because pi over 3 belongs to the range of arc sine. But in just a little bit, we're going to see problems where it's not quite so clear cut. So I want to get used to drawing these pictures. You're going to need them again in a moment. Our next example, calculate tangent of tangent inverse, tangent of arctangent of pi over 3. Now, once again, there's something important to recall, so I'll go ahead and put that here. Remember, from page 2, when I take tangent of arctangent of A, we get A again, as long as A belongs to the domain of arctangent. It's between negative infinity and infinity. Now, in this particular case, that makes things really easy. Again, we really don't have much to worry about. This just says A has to be a real number. Well, is pi over 3 a real number? You betcha. So when I come over here and write the answer is pi over 3, the tangent and the arctangent undo each other, and I'm simply left with whatever A was. That's all there is to it. But now is when things are going to get a little bit tricky, and this is where we're going to have to start paying attention to things because it's not always this clean. For example, check out this problem right here. Cosine of cosine inverse of pi over 3, calculated if it exists. You'll notice I've put the hint if it exists here because I'm not going to be leaving you in suspense for very long, and the answer is it doesn't. Here's the basic reason why. Recalling from page 2 that cosine of arc cosine of A is equal to A if A belongs to negative 1 to 1, we now really have to ask ourselves a question. We know that pi over 3 is a real number, but is it in this interval? Well, actually, a quick estimate will show us it is not. It's an easy one, too. When looking at the number pi over 3, I happen to know that pi is bigger than 3. It's 3.1415926, etc., etc. So, what I could always do is say, hey, listen, if I have the fraction pi over 3, you know it's a smaller fraction? 3, instead of pi, over 3. And guess what? 3 over 3 is equal to 1. So, there is no answer in this case. We've picked a number that is outside of the domain of arc cosine, so this does not exist. There is no answer. You have to watch out for that. Some of them, like for example, tangent, are very easy to deal with and they don't have this problem very frequently. Some of them, like cosine and sine, have them a lot. You have to pay close attention to what you're writing down. Here's another interesting problem for you to work with. This time, we want to calculate cosine inverse of cosine of 4 pi over 3. Now, at this point, many of you probably looked at the problem and said, oh, obviously, the answer is 4 pi over 3. But in fact, this is wrong. It is not 4 pi over 3. The reason why is that the equation that you're thinking of, the cosine inverse of cosine of an angle, gives us the angle back, only works if the angle is in the subdomain for cosine, in the range of arc cosine, which we know is 0 to pi. Is 4 pi over 3 in 0 to pi? Well, let's graph it really quickly. Now, if you recall, and it's a trick we've used plenty of times, 4 pi over 3 can be rewritten. It's both a measurement of radians and an arc length on the unit circle, and for that reason, we can rewrite it as 4 over 3 times pi, and it still makes sense to us. If you look at it this way, this means that when we go through the arc to make the angle 4 pi over 3, we're going to go through an arc that's 4/3 the length of pi, or in other words, slightly bigger than pi. So what we're really talking about, in fact, is an angle that falls into quadrant 3. This right here is 4 pi over 3. I recommend you double check me when I say things like that, but you'll quickly find that it's the truth. Okay, you say, this is a problem. I don't know what the answer is going to be then. I know that cosine of 4 pi over 3 will give us answers down here. You can actually figure out what this terminal point is, and I will leave that to you guys to think about. The hint I would give you, if you want to use that, is to look for a reference angle. And you will notice, if you start working your calculations here, that since 4 pi over 3 is bigger than pi, the reference angle can be found by taking 4 pi over 3 and subtracting pi from it, which will give us pi over 3. But there's actually an easier way to do this than to worry about calculating cosine of 4 pi over 3, and then trying to calculate cosine inverse of whatever number we get. See, here's something that we know, and we've talked about many times. If I have an angle, and I reflect it across the x-axis, like I'm about to do right now, like this, even though there are going to be some changes, we're now no longer below the x-axis, we're above the x-axis, so that means that we went from a negative y value for our terminal point to a positive y value for our terminal point. Is there any change to the x-coordinate? No. The x-coordinate for this blue point is exactly the same as the x-coordinate for this red point down here. In fact, if I were to start calculating, you'd very quickly find out that if I take cosine of 4 pi over 3, or cosine of whatever this blue angle is, I will wind up getting exactly the same answer. So now, here's the only question. What is this blue angle? Well, because of the way that I've reflected things here, the blue angle and the red angle should have exactly the same reference angle, which is to say, the reference angle here should be pi over 3. And I'll bet you dollars to donuts if you realize that the angle that I'm interested in is an angle in quadrant 2 with a reference angle of pi over 3, you will quickly figure out the right answer. It should be that this blue angle is 2 pi over 3. Why is that significant? Because now I can rewrite this problem. What I'm going to do is the following. I'm going to still write cosine inverse of cosine of some value, but because I know that cosine of 4 pi over 3 and cosine of 2 pi over 3 give me the same answer, they correspond to coordinates of points with the same x-coordinate, there is no difference between writing what I was given and what I've written here in blue. Now I'll ask you this. Is 2 pi over 3 in the subdomain for cosine? Is it in other words, the range for arc cosine? You betcha. And now the property from page 2 applies. These two functions undo each other, and I'm simply left with 2 pi over 3. Let's do at least one more problem before we call it quits. This video is getting plenty long, but I want to make sure that I have as much information in front of you as possible, and I want to make sure I practice this skill again. So I have another exercise for us. Almost the same, but this time we're calculating sine inverse of sine of 4 pi over 3. Well, I already know that I'm running into the same problem here that I did up above. 4 pi over 3 does not belong to the range of arc sine. So I can't simply say the answer is 4 pi over 3. It does not work that way. That means I'm going to have to do some rewriting again. So here's what I'm going to do. Just like last time, I'm going to go ahead and draw the angle. So let's do that really quickly. Okay, we have 4 pi over 3 drawn again, and because we've already talked about this, I've noted the reference angle for 4 pi over 3 is pi over 3. Now, last time, what we did is we said, hey, listen, I'm going to rewrite my equation because I happen to know that cosine of 4 pi over 3 and cosine of 2 pi over 3 are the same. The reason being, they are reflections of one another across the x-axis, and an x-axis reflection does not change the x-coordinate. In other words, it does not change cosine. Unfortunately, we saw in the same example that the x-axis reflections do change the value of sine. Sine down here at 4 pi over 3 is negative, sine up here at 2 pi over 3 is positive. But there is another type of reflection we could do, and some of you may have already figured out this is what was going to happen. If I reflect across the y-axis this time, notice the x value changes On one side it's negative, on the other side it's positive, but does the y value change? No, it does not. Symmetry of the unit circle tells us this is going to be a point that has the same y-coordinate as our red point over here. We also know that when we're talking about sine, sine is restricted to the right-hand side of the unit circle, so we're in the right spot, and to get down into quadrant 4, we have to go in the negative direction. Plus, my red angle and my blue angle must have exactly the same reference angle. So, doesn't that mean that the reference angle here is telling us that this angle here is negative pi over 3? Yes, it is telling us that. So how do we rewrite this problem? Well, we write exactly the same expression that we were given, except that we say, hey, listen, I don't need to take sine of 4 pi over 3. I would get the same answer if I took sine of negative pi over 3. Now I've rewritten the equation. It's not going to change my answer. These two things are exactly the same. But now that I'm looking at this second equation, notice that the angle on the inside is an angle in the range of arc sine. Since we are now looking at arc sine of an angle, and the angle obeys our rules, now I can simply let arc sine and sine annihilate each other. And so the answer becomes negative pi over 3. And with that, I think that's almost all the time we have. A couple of quick notes. For my students, you may be wondering what other problems there might be in this section that you need to worry about. The only other ones that we have not touched are feeding values to arc sine, arc cosine, etc. on your calculator. Now, because of the way this video format works out, I can't really show those to you in person. However, if you have the TI-30X2S, first of all, notice that when you're looking for these inverse trig functions, you should find them by locating first the original trig functions like sine, cosine, etc., and then simply hitting second followed by the appropriate trig function. So if I press the second button on my calculator and then sine, I should be dealing with arc sine now, no problems. The next thing I want to address is that there are more identities. I mentioned earlier that there were equations that I wasn't going to be showing because I didn't find them to be as useful, and I showed you why. I also have some other ways and some other relationships we can use. You may be wondering, for example, could I do a similar trick to what I did in these last two examples if I worked with tangent? Yes, there is a trick for working with tangent as well. However, we've run out of time. I feel like an hour-long video, which we pretty much have here, is plenty long enough. Instead, I will give anybody who wants to a chance to ask me questions, either in the comments section of this video or in Canvas, where USF holds its classes. For now, that's all the time I've got. So, everybody, thank you so much for your attention. Thank you for your continued hard work. If you have questions, feel free to reach out to me. And until I see you next time, happy math.